What questions do you have?
We don't have a quiz this week.
We do not have a quiz this week, correct. We don't have a quiz next week either because our test is a week from Thursday. A week from this Thursday, yes. We'll chat a little bit more about that on Thursday. It's looking right now, it should go up through probably 4.2. We'll get through 2.6 today and what I want to do in chapter 3. And then we might start chapter 4 today, but if not, we'll definitely start it on Thursday. So we're going to do a little bit in it. It's just modeling. So we'll talk about how to set up a couple of models, but in general, I try, although it's probably the most important component of differential equations, I need to get through the techniques so that you can actually apply them to models later. So it's a trade-off. So I try to do a little bit of it to keep the motivation in mind, but mindful of all the extra stuff we still need to get through this semester. We're already in week 4. It's crazy. It's absolutely crazy. So be over a quarter of the way through the semester by the end of the week. So not what you wanted to hear, was it? Or maybe it is. Maybe you're ready for May and be done. So, all right. Anyway, any questions at all before we continue on? Things going all right? All right. Well, let's do one more substitution example. See if we can figure out what we might want to do with this one, just to kind of give you another. It just mirrors that way off. It seems to be getting worse. Try that. We've had a couple of different substitution techniques that we came up with for a couple of particular types of equations. We had the homogeneous ones, where we said we looked at the individual terms that appeared with the x's and y's, and if they had all the same degree, then we made the substitution y equals ux and played around with that. We also said that if we had it in that special form, so I'll just flip back to last class rather than saying what it is. So last class we talked about the form, that one, where it almost looks linear. It's that piece right there that makes it not linear, right? So we basically moved it to the other side and made a substitution so that it would look linear, right? So just to mention that in general, if I move this to the other side, then this piece right here almost looks like the derivative of that piece right there, right? So if I differentiate this piece right here, then the power decreases by 1 and I get the other one. So I can get that product rule kind of thing set up over there, right? So we started it off by saying that u equal y to the 1 minus n, and then du was, I'll even write it as du dx, was 1 minus n y to the y to the negative n, dy dx. And then when you make your substitution, then you've got 1 over 1 minus n u prime plus p of x u equals f of x. And now we've got something that's linear. That was the substitution we made for Bernoulli. So let's see if we do another one where perhaps the substitution isn't as clear, but think about what we might want to try to do. And sometimes it's just literally try. So this is, I didn't label it. This is number 26. We don't have a lot of techniques, right? We've got 3 that we've learned so far, and then we've made substitutions to make them look like one of those 3. Actually, we made substitutions to make them look like one of the 2, right? We don't have a lot that we can do right now. So this is not separable. Sine of x plus y, there's no way to separate it, right? Certainly not separable, certainly not linear because it's sine of x plus y, okay? And probably not going to be exact because your partials aren't going to match. If you try to rewrite it and make your partials match, they're not going to match. So doesn't really fit one of the things. So again, the idea with the substitutions is to try to make it, the whole idea is kind of like what you do with U substitution or trig substitution or integration by parts. You try to make a substitution to make it look like something else, right? Make it look like a form that you do recognize it, okay? So at least in this particular one, I would say it's this thing that's making the issue, right? So let's just try to make a substitution to start with that and see what happens. That's the best thing you can do is just try something, right? If this were, and this is motivated by trying to make it look into a form that I know how to work with. If it were sine of just u, it would be separable, right? Okay, so let's try to let u equal x plus y and see what happens. And it may not work, who knows? We're just trying, right? Okay. If we did that, that would be y equals u minus x, right? What would our dy dx be in this case? We think of y as a function of x, but we're also thinking as u as a function of x. So if I do dy dx, what would I get for that on the right-hand side? Okay, so the way I've got, you're right. If I write it as differentials, you can do it that way too. The way I have it written, it would be a du dx minus a 1, right? Or like Trey said, if I write this as differentials, I can also think of it as dy as du minus dx, right? You can do it that way too. Either or. So let's see what happens when we do our substitution here. Dy dx is du dx minus 1. And the right-hand side is sine of u. Right? Let's rearrange it a little bit. Du dx is sine of, gosh darn it, sine of u plus 1. And rearrange, now this is separable. I get, good grief, if I could write, sine of u plus 1 du equals dx. This is not, it's 1 over that, isn't it? It'd be a lot easier if it were just the other. Is that okay? All right. Now it's actually separated, so the hard part would be to get this integrated. So they have this one in here. They do not. Okay. Sometimes in the front cover of the book they have them just written out, so we don't actually have to go through it all. Oops, I forgot to integrate, didn't I? I wrote an x dx because I was integrating as opposed to an integral sign. Good grief. All right, let's see. I can wake up. All right, the right-hand side is just an x plus c. That was why I jumped ahead. Sorry about that. All right. Thoughts about how to do the thing on the left-hand side? requires a little bit of clever trig. Maybe instead of writing it as, maybe this kind of shake loose an idea. There is 1 plus sine of u. Can I multiply top and bottom by something where it allows me to rewrite the bottom as a single term? Think of your trig identities. Not quite the reciprocal, but I think you may be thinking about it along the same lines. If I had a 1 plus a square root of x in there, what might you multiply by to try to get rid of the square root? At a 1 plus square root of x, what might you try to multiply by? If I try to get the, I want the root to go completely away in the denominator. If I just multiply by root x, it'll distribute. It's been a while since you've done it. You do it in algebra class. What's probably the most famous identity that you know for trig functions? Yeah, sine squared plus cosine squared equals 1. And if I rearrange it, what would 1 minus sine squared equal? Cosine squared. Can you do something with that to get a 1 minus sine squared? There you go. Multiply by 1 minus sine. Exactly. Do that. It's a conjugate idea, right? Remember, if you had a 1 plus root x in the denominator, you might multiply by 1 minus root x because you get 1 minus x, which is 1 minus x in that case, when you multiply it out, right? So on top, we'll get 1 minus sine of u. What do you get on bottom when you simplify? Which is cosine squared. Good. Now, why does that help? What can I do now that I couldn't do before? Well, I could do a u sub. That's overkill. The plus sign was in the denominator before, and I got a minus sign in the numerator. What can I do now that I couldn't do before? I can separate it, right? I can now separate it into 2 pieces. You can do a u sub, by the way, or a double u sub probably in this case, but that's overkill. You really don't need to do that. 1 over cosine squared is secant squared of u. Sine over cosine squared is sine over cosine, which is tangent, 1 over cosine, which is secant. So this is minus secant u tangent u du. And this is why you didn't need to use u substitution. What's antiderivative for secant to u, or secant squared to u? Tangent. And for secant u tangent u, it's going to be secant. And now we can finish it off. Because u was equal to x plus y. We get that. A little tricky, but it just gives you an idea of another way that you could do a substitution. What was the motivation for our substitution in this case? I hate the x plus y, so I made it go away. Right? That was the entire motivation for the entire substitution. I don't like it, so I'm going to make it go away. And it did. Okay. So a lot of times, well, I won't say a lot of times, if you look at the other types of problems that are in that little subsection in the text, these are 23 through 28. If you look at those, it's literally, okay, here's a chunk that's inside a composition. Let's let u equal the inside, which is not uncommon to you because you've done that for u substitutions, right? It's kind of the first try for u substitutions. If I see a composition, let u be the inside. Right. Any questions on that one at all? Okay. All right, so let's actually continue with that particular problem, but let's do it from a numerical standpoint. So let's say that we wanted to change this to an initial value problem. Let's say we want to consider dy dx equals sine of x plus y, but y of, oh, doesn't matter. Let's say y of 0 equals 1. Let's start that way. Now, we have an exact solution that we could do and figure this out. But what if we didn't have an exact solution to start with? Well, there's a method that we can use, actually a relatively straightforward calculus 1 idea that we can use to try to figure this out. Okay? Or at least give us an approximation that hopefully is fairly decent when we're close to the initial condition. The farther we move away, the worse it'll probably get. Pardon me. But this is really a straightforward way to get us a numeric approximation to a solution from one point to another point. Okay, and this is what's referred to as Euler's method. And it really is a straightforward concept. Okay. Let's say we have a solution curve, whatever it happens to be. Okay. We start with a first order differential equation. We write it in that normal form where we have it solved for y prime. Okay. So the right-hand side is a function of xy. And again, we have some initial condition. Let's say when you put in x naught, you get out y naught. Now, what calculus 1 concept do you know that allows you to get a fairly decent approximation to the curve as long as you're close to the initial point? What calculus concept do you do? So one of the first things you do in Calc 1. Say that again? Tangent line, exactly, right? The tangent line's a good approximation as long as you're close and your function is differentiable, right? Okay? Your tangent line's a good approximation. So that's the idea. When we're close to the point of tangency, the tangent line's a good approximation, right? Of course, the farther away you get, it gets worse. So what are we going to do in this case? We're going to do one step after another. We're going to do a multi-step kind of idea that's going to allow us to find an approximation, go out a little bit, stop, find a new approximation, go out a little bit, stop, and continue this idea. Okay? So what we'll do is we will follow we'll follow our approximation line for some little step. Oh, my goodness, sorry. And the idea behind this, hopefully, is that those 2 points are close together. We hope that our, for heaven's sake, stop. Hope that y of x naught plus h is close to what? Well, how did we get to that next point? this part right here would be your y of x naught plus h. What's the y coordinate for this one? Okay, well, let's step back. How do you find the equation of the tangent line? Yeah, okay. What's the derivative give you? Well, for the line, what does the derivative give you? For the line. With respect to the line, the derivative gives you the slope, right? So your tangent line, the slope will be dy dx evaluated at what point? Oops, let's write it this way. It's the derivative evaluated at what? Well, for the tangent line to start with. Not x naught plus h, but just what? It's just the x naught, y naught, right? What gives you the derivative at x naught, y naught? What gives you the derivative at x naught, y naught? The function, right? The function gives you the derivative value, right? So our slope for our tangent line will be f of x naught, y naught, right? That'll be the slope. But I still need to fill in the other pieces, right? Right? What other pieces do we need to fill in? We don't just need slope. What else do we need? Is it a plus? It's a minus x naught, right? Y minus y naught. Remember your point slope form? Yeah. Okay. All right. All right. So how do we use this now to give us that? Well, we already have the f of x, y. Now we're using the tangent line, right? We're using the tangent line to get to the next point. How do I find the y coordinate on that line? By putting in what? I agree with you that we need to solve for a y, but what do we need to plug in? X naught plus h, right? The x value that I'm interested in, right? I want to figure out what the y coordinate is above where I have x naught plus h, right? Okay. So what do you get when you put in x naught plus h? Well, what happens in here when you put in x naught plus h? What do you get? Just h, right? So the y coordinate up here will be y naught plus f of x naught y naught times h. And so this is what these two pieces should be approximately close to each other. Okay. All right. So we've moved one step. So let's recap what we just did. Okay. Because we're literally going to do the exact same process again. Okay. So as long as we understand what this process is, the next pieces should go faster. Okay. What did we do? I have a differential equation. I have a differential equation, right? I said, okay, rather than knowing what the solution curve is, I know where I'm starting. I have an initial condition. That's pretty fancy, wasn't it? I have an initial condition. I'm going to use the tangent line to the solution curve, whatever it happens to be. I don't know what it is, right? The whole point of this is to solve. Okay, I'm going to use the tangent line to go from one point to the next to give me an approximation of what the next point should be. Okay? Now I'm going to say, okay, that blue point that I've drawn on there is now on the curve. It's not quite, because I've approximated the point on the curve with the tangent line, right? It's not quite, but it should be close. If that's points on the curve, literally do the exact same process again. Okay? Assuming that point is on the curve, we will find the tangent line at that point. The tangent line at that point. It's not quite on there, right? Right? But I can approximate what its slope is because I have a function that says if I have an x and a y, I can get the slope. Right? Right? So we're going to find that line and say it's my approximation to the curve. We're going to move over a little bit and then find this point. And then continue this process and get a bunch of sticks that approximate the curve. Okay? So here's what the algorithm looks like. You start with the point x naught, y naught, and choose a step size. That's the first step. Okay? We find y sub I plus 1, the next step, is going to be the previous y value plus f of the previous x value, comma, the previous y value. Your xi just changes by adding h each time. Okay? And you stop when your y sub I, your x sub I is equal to the target x. I'll put it in quotes. You're always going to try to estimate what y of an x value is based on a starting value. Okay. So the easiest way to do this is Excel. Okay, so let me just show you how to do it. You can do it by hand. On an exam, I would expect you to do a couple of steps by hand in a calculator, but like I said, the easiest way to do this is Excel. Okay, so let me just show you real quick how you would do that in Excel. Why is that not? There we go. All right. So this will load. There we go. All right. So when I type these things in Excel, I typically label the columns. All right. So our n here will just be the step number that we're on. Okay. We always start at step 0 because that's our initial condition. And then if I just put in 0 and then 1 below it, if you haven't done a lot with Excel, there's quick little tricks that you can do, and many of you have already heard this if you've had any numerical. I highlight these two that form a pattern. Notice my cursor changes size when I go over here to this little black box that's in the right corner. And if I drag, then it just starts counting it up. Okay. All right. Here's where I'm going to put my h, whatever my step size is. And again, you're going to choose that. Okay? You'll choose what the step size is. Then you'll have an x sub n and a y sub n. In the first row, those will be your initial point, right, wherever it starts. Okay. I'll just put in another column in here for what the derivative calculation is. So I'll call it f of x sub n, y sub n. I probably could have called it I rather than n, but whatever. And then this will be your next one. So I'll call it y sub n plus 1. Okay. All right, so let's write down what the original, goodness gracious, what the original differential equation was. It was dy dx equals sine of x plus y. And I said that our initial condition was y of 0 equals 1, right? So going over here for my h, let's just start with 0.1. The original x value is a 0, and the y sub n, the original y value was a 1, right? Right? Okay, so just type those in. This is the beauty of Excel. I'm going to have to type in one thing, and then I'll do copy and paste, and it'll fill in everything else for us. Okay? So this is what the derivative at that point should be. So the derivative is supposed to be sine of x naught, y naught. Okay? So again, if you're comfortable with Excel, this should make sense to you. If not, let me just tell you what's going on. If I'm going to do a formula, I need to start it with an equal sign. The sine function is built into Excel, which is nice. And then I'm going to do these with relative cell references. So this is going to take the sine of whatever is 2 to the left. And then, oh, I need a plus sign. I put a comma. That should be a plus sign. 2 to the left plus 1 to the left. Those are relative cell references. I need to change that to a plus sign. It'll give me an error if I hit enter at that point. Okay. Are we comfortable with typing that in? Okay. And now over here, what did we say the formula was for the next y value? It was the previous y value, which is over here at D2, plus the derivative times the step size. And notice I'm just clicking on the cells that I want. Okay? So far, so good? Okay. Okay. Now here, this will be your steps. Oh, sorry, this is easy. Your step size is always, I should do it this way. Your step size is always the same, but I'm going to say equal to the previous cell, because if I want to change the step size, I can just type in that first cell and it'll copy it all the way down. Okay? So I'm just going to say that's equal to the cell right above it. So that allows me to change it easily. Oops. This is previous x value plus the step size. That's how we find our new x's, right? We're just going to step over the same amount every single time. The new y value is the one we just calculated. So that's up there at F2, F2. And now everything else is copy paste. Okay? We're done typing. This is literally the last thing we have to type. Okay? All right, so here I'm going to highlight these two cells, copy them down one row, and then I'm going to copy all of these cells and copy. Boom. There we go. That gives us an approximate solution. If you want to see what this, if you want to graph what this approximate solution might look like, Excel is okay with that. Let's say I wanted to approximate what y of 1 is. And so the approximate value here would be 1.822-ish, right? Okay. If I wanted to see what a graph of that might look like, you could insert a chart. And in particular, if I do a 2D line chart, there's what the graph kind of looks like. Just kind of nice. We'll come back to that here in a second. Again, the idea behind this is now, if you wanted to reduce your step size, because reducing the step size should give you a better approximation, I can do that quickly. I can just say change this to 0.05, and it changes all of them. And notice now that I have the chart in there, it also changed my graph, which is kind of nice. Although I cut it off at a half. It's pretty flat. Right. Does process make sense? We're going to come back to this in here. I'll do another example or two here. Does the process make sense okay? Yep. Okay. Going back here real quick to the original problem. We solved it earlier, right? This was the solution. A little hard to get the initial condition here, but let me graph this without the plus C on the end and see if the shape looks okay. Desmos will plot this implicitly. Was tangent of x plus y minus secant of x plus y equals x. We got lots of copies of it, right? But we did from 0 to 1 in that first instance. Here's what the graph looked like. Let me go back over to Excel real quick. See if we can put these side by side. Ish. Hide that. Let me change this back to 0.1 so we actually get up to 0.1 here. There's what the graph started to look like. It was starting to bend down, and we can see that bend down here, right? Right. If I go, maybe just go a little bit farther here. Let me delete this chart and make it go all the way to, say, 1.5. Here's 1.5. It certainly started to go back down again. And you can see it started to bend. Right? So it's going up and starting to come back down again. So it's giving you a halfway decent approximation, right? Not exact. But it shouldn't be giving you exact, right? Because what are we approximating with? Tangent lines. We're doing sticks, right? We're trying to get an approximate solution to the curve using sticks, which we've done a pretty decent job of in this case. The reason why it's pretty decent is because your sine of x plus y is pretty well behaved. What is your derivative always in between if it's sine of x plus y? The sine of x plus y, what's the derivative always going to be in between in this case? Close. That would be the positive side. 1 and negative 1, right? It's going to bounce between net 1 and negative 1, right? So your derivatives are going to be well behaved. So it should give you a relatively decent approximation. If your derivatives aren't particularly well behaved near a point, then you're going to get some problems. That make sense? Okay. So let's see if we can do some other ones here that are examples out of the book and see if we can kind of compare the two. So let's look at what these that I did. Let's look. This is number 4 in your text in section 2.6. First thing we're going to do in 2.4, or this one, sorry, number 4 in 2.6. We've got the equation y prime equals 2xy, and the initial condition is y of 1 equals 1. We're going to use Euler's method here to do some approximations, but I also want to compare it to the exact solution. Okay, so let's see if we can do the exact solution first. What method might you choose here to do the exact solution? Yeah, separate it, right? So if we separate this, we would have 1 over y dy equals 2x dx, right? When you divide the y over, move the dx over. And now integrate both sides. Antiderivative for the left-hand side is what? Yeah, natural log of, technically it's absolute value of y, but notice our initial condition, we're going to use a positive y value, so I'm just going to write it as natural log of y. Antiderivative for 2x is x squared plus a constant. I'm going to do the initial condition now, and then I'll solve it for y. If you plug in 1 for y, natural log of 1 is 0, X is 1, 1 squared is 1, so you should get c is negative 1, right? So if you use y of 1 equals 1, gives you c is negative 1. So if we solve this, we'll get y equals e to the x squared minus 1. If I undo the natural log. You should be able to check that that satisfies the original initial value problem. Certainly it satisfies the initial condition. If I put 1 in for x, I get e to the 0, which is 1. If I differentiate the right-hand side, I would get a 2x e to the x squared minus 1, and e to the x squared minus 1 is y. So I get a 2xy. All right. So good little review for separation of variables, right? That's not too bad. Okay. But the reason why I wanted to solve it is because I want to compare our approximations to the actual values of the function. Okay. So the problem in this case asks you to approximate y of 1.5. That's the actual directions of the problem. It wants you to approximate y of 1.5. Okay. So let's hop back over to Excel. I'm going to open a new sheet to do this sheet. All right. So again, I'm just going to write the problem down so we know what it's asking. dy, or I'll write it as y prime. Y prime equals 2xy. Y of 1 equals 1. We want to approximate y of 1.5. And we already know that the exact solution is y equals e to the x squared minus 1. Right? Okay. So just to set this up again, or you can use the same sheet that you were in, it doesn't matter. I'm just going to do n h x sub n y sub n. I can type f of x sub n, y sub n, and y sub n plus 1. All right. Yeah, I'll go ahead and copy all the way down there. Oops. It says first use h equal to 0.1. Those are the directions. It says first use h equal to 0.1. Our initial x value is what? 1. Our initial y value is 1. Over here, what is our f of xy for this problem? Yeah, 2 times xy, right? Remember, this is your f of xy, right? The right-hand side. You put this in normal form, right? dy dx equals something with x's and y's, okay? So what should go here in the cell then? Good, 2 times c2, which is where the x lives, right? Times d2, which is where the y lives. Everybody okay with that? Okay. Do you think you could also do a problem like this on the calculator for a few steps? Okay, cool. All right, what goes here? How do you find your new y value? Good. Old y plus slope times, oops. Yep, that's about right. Times the enter key and the shift key are too darn close to each other. Times the step size. All right. We started our point of tangency and we follow the tangent line for the step size. The y value tells you where to start. The slope tells you the direction. The step size tells you how long you go in that direction. By the way, That is a fundamental concept in what's referred to as gradient descent for optimization problems that work in neural networks. It's literally that. Where to start, which direction to go, where to stop. That's literally gradient descent. Okay. And if you don't care about neural networks, then you ignore what I just said. Okay? But that's literally what gradient descent is. Okay? Pardon me. All right. Is that okay? And the rest is just copying. Remember, again, we want to copy down the step size because we won't be able to change it easily. Our next x is our previous x plus the step size. So it's just C2 plus B3 in this case, but it's literally previous x plus the step size. Oh, stop. Why did you put a circular reference in there? Probably because I hit the arrow key. What goes here? Yeah, the F2, right? We're going to copy down the new y. Okay. And now we just copy everything. Copy that down a row, highlight the entire row, and I'm just going to pull it all the way to the bottom. This problem asked for what? It asked for x of 1.5, or excuse me, y of 1.5. What's the y value associated with x equal to 1.5? Say it again. About 3. Yeah, it says 2.928, right? This one here is literally side by side with the 1.5, right? These are the points that should be on the curve, or close to the curve. Okay. One of the reasons why we figured out the exact solution in this case is so that we can compare, right? So here, let's do, I'll just label it as exact. I'll call it exact y's. Okay. This is going to be E of, if you want E, well, you can't just use E. You have to use the built-in EXP function. I want E of the X squared minus 1, like that. So I did an EXP of C2 squared minus 1. Right? So there's 1. Now, of course, they're going to match. It was the exact solution at that point, right? We haven't used any tangent lines, correct? But now we should be able to pull this down and see some differences. In particular, look side by, kind of side. You kind of have to diagonal a little bit. Here we did, these two are a little bit off. These are more off. These are more off. These are more off, right? These are the ones that should match. Are kind of diagonal down one spot. Will we have it written? Yeah. Okay. We could do, if you wanted to, relative error. How do you do relative error? Do you remember how to do relative error? I got science people in here. You got to know how to do relative error. How do you do absolute error? What does error mean? Start there. Difference. Good. Difference between your observed minus your true value, right? Essentially. Yeah, so it's the same idea here. So we'll do absolute value of, this was your observed, this is your true value, right? That would be absolute error. If I want relative error, what do you divide by? You observed minus true over true. Good, thank you. You had a 50-50 shot, right? It was either true or observed, right? That's relative error, right? People do experiments. You're going to have to look at, you're right, lab reports, right? You're going to do errors. Yes? You're all shaking your head yes, and I'm not sure I believe you. All right, anyway. Obviously, that relative error for the first one should be 0, but if I copy it down, it should get bigger as we go. And those are percentages, right? So I'm at about 3%, and then 6%, and then 10%, and then so it's getting worse as we go, right? Theoretically, we should be able to make our errors better by shortening our step size, right? So the other part in this problem said to do 0.05 instead of 0.1. Here now is our approximation for y of 1.5. And notice that the error is about 10%, but it's better than it was, wasn't it? Previously, just if I switch it back over, previously the relative error was about 20%, 19%. We have the error size, 0.5. We have the relative error. Okay. We should also be able to look at those graphs again like I did before. So here was, let's just do that part. Come on. Insert a chart. 2-dimensional. There's what the solution curve looks like. I should be able to remember how to do this. Let's select some data. Let's add a series. And the series that I want to add is I can't move that out of the way. All the way down there. Can't see it, but there we go. Should add it. See if that worked. Whoa. What did I copy over? That shouldn't be that far off. Oh, it didn't do the X's right. Sorry. I know why. Let me go back and fix this. Select data. Edit. Series X values. I didn't pick the X values that we wanted. There are these. There we go. There it is. So the orange is the exact solution. Well, not quite. What did I grab? Oh, I grabbed the wrong one. I want these to be G's. Try one more time. Sorry about that. There we go. The oranges are your exact solution, and your blues are the approximate. So you can see it starts off close, but then it starts to break apart the farther you go. Which makes sense, right? Because again, we're trying to do sticks at each one. And each stick isn't actually on the curve. What we'll do later in the semester with another technique is to, okay, we're going to move a little bit with the tangent line, and then we're actually going to move back up and try to be tangent again with the new slope and try to do some averaging things. That's what's referred to as Runge cutout method. We'll talk about that later. Is this process okay? Like I said, I'm only going to expect you to do a few steps by hand with a calculator. I'm going to expect you to reproduce Excel on the exam or write any Python code or anything along those lines. But I didn't want to show you what it looked like. Is this okay? All right. Let me give you just a couple of practice problems out of this. And then we'll get on to some modeling things. So from 2.6, did I give you ones out of 2.5? Yeah, okay. 2.6, I want just 3, 7, and 9. Just those 3 problems. Okay. You're more than welcome to practice them with Excel, but again, make sure that you can do them by hand. At least for a few steps. As long as you can do the first few steps, that's fine. I'm not going to make you do like more than 3 steps. Because it gets repetitive after a while. All right. If you can do 3 steps, you can do 10. There's no reason why, right? That's just going to try to introduce more error. All right, so let's talk a little bit more for the rest of the time with modeling ideas. We've already done a little bit of this stuff before. But just to talk about where different things come from, we've already mentioned things like population growth or exponential growth or exponential decay. I'm not going to spend a lot of time on these. Oops. We're going to just talk about the premises where some of these come from. If you happen to go to the candidate talk last Monday, she did mathematical biology things. She did what was referred to as a system of differential equations. Most of them, well, if I remember, were actually linear ones, but it was the same kind of concept. You're going to have a rate of change that depends on how much is there at a given time. And she actually went through a nice example of how things were changing over those times. So this modeling stuff comes up, and these relatively straightforward ideas lead to complex models, especially when you have things start interacting with each other and come up with what's referred to as a system of linear equations, a system of differential equations, which we will do some of that as well this semester. But these simple ideas can lead to modeling of complex systems fairly accurately, it turns out. Exponential decay and growth all come from the same idea. The rate of change of some quantity is proportional to the amount of that quantity. And the fundamental differential equation that pops up from that assumption is just y prime equals k times y, is proportional to y. It's probably the most straightforward differential equation model that you come up with. In fact, when you analyze how well a numerical method works, you come back to this type of problem. They refer to this as the model problem. It gets more complicated than just, you can think about it in terms of a system as well. If the derivative of the system would be proportional to the system, which you just have a matrix equation in that case. So it wasn't a matrix equation in that case. But again, analyzing things like stability of a method, is it gonna, if you tweak the input slightly, is it gonna make the answers blow up and not converge? That's stability ideas. Come back to this problem. So even though this is, again, probably the most straightforward idea, this does pop up in more complicated ideas later. Okay? Just so that you know where things are going. The nice thing about this one is it's not too hard to figure out what the solution is, because the function that we know is that is a multiple of its own derivative is exponential, right? So this becomes y equals e to the kx. And then you have some initial amount present. This is a lot of times your books will use like a sub 0 or a naught as the amount present initially. You've seen this before. You've seen this model before you even saw derivatives, probably. Okay. Another model that pops up is Newton's law of cooling. What does Newton's law of cooling say? Or, even if you don't know necessarily what it says off the top of your head, what makes sense? If I take something out of an oven, is it going to cool faster when I first take it out or later on in the process? When you first take it out, right? So again, the change in temperature is going to be proportional to something about the difference of the temperatures, right? Okay. So it looks a lot like your exponential growth or decay. It's just that I'll write it as temperature dt. It's proportional to whatever the temperature of the object is minus the temperature of the surroundings. Okay. So T is the temperature of the object. T naught is temperature of the surroundings. And again, it makes sense that it's that proportional idea to it, right? If the difference in the temperatures is large, then the change in the temperature of the object should be faster than if they're closer together. Doesn't that look like exponential growth or decay? It's just shifted, right? So same kind of idea. So you can come up with a general form of this too, which is not that bad, because this is a separable differential equation, so it's pretty quick. Okay. So these again are a couple of straightforward models that you probably have seen, may have seen, not too hard to figure out. Well, the second one from the first one, right? Okay. We did another one where we did mixtures, right? So remember, just to remind ourselves of what a mixture problem looked like. Let's see if I can come up with one. Let's look at one of these. Oh, I did that one. Okay, so this is actually, it's number 27 in your text. 27 it's a 500-gallon tank that's full of pure water. Brine with a concentration of 2 pounds per gallon is pumped in at 5 gallons per minute. And the well mixed solution is pumped out at 10 gallons per minute. We've set up problems like this before, right? And the setup behind this, again, if you went to the candidate talk last Monday, she did an exact setup just like this, right? You have stuff coming in, stuff going out. The difference between those two is the change, right? So let's say Y is the amount of salt at time T. You're going to do rate in minus rate out, right? Right. How much, and again, Y is the amount of salt. How much salt is coming in each minute? 10 pounds, right? Where'd the 10 come from? 2 pounds per gallon, 5 gallons per minute. We want to end up with pounds per minute when we're done. Multiply, we get pounds per minute, right? This is where the well-mixed solution pumped out comes at, right? Since it's well-mixed, we assume that the concentration of salt is the same no matter where you are in the tank. Now, these are things that you actually have to worry about if you're doing modeling. That works nicely for us to be able to solve this problem, but in general, What does well mixed mean? Is the salt going to tend to fall to the bottom of the tank? So if the drain is at the bottom, there might be more salt coming out at the beginning than at the end. If you're somehow siphoning it off from the top and following the water level down, it might be less salt coming out at the top than the bottom, right? Those are assumptions that you have to make. Now, that's a weird case because I'm talking about salt in tank, but drug concentration in a bloodstream, that may not be constant, right? And certainly the drug may not be well mixed through your bloodstream, especially initially, right? If you're modeling certain things, or not necessarily drugs, you could do hormones going through the body, right? What the candidate, I keep going back to the candidate, it was a nice representation of how you can apply differential equations to a particular field. Was worried about stress effect on ovulation. There's hormones going on, with the stress effect of those hormones. But again, you can imagine that hormones being secreted in the body, again, isn't going to be necessarily well mixed to start with, right? So you may have to tweak things to make your model work. Anyway, this is where the well mixed part comes in. Sorry for the little diversion there. Again, I'm going to do a multiplication. How much salt is in the tank at time t? I don't know that, so we denote that with y, right? And then how fast does it go out? Yeah, 10 gallons per minute, right? And there's one more piece that we need. Y is the amount, but the concentration will be how much is in the tank, right? And so in this case, it should be 500 minus 5t, a little bit of a tweak there. Why do I have 500 minus 5t there? Where'd the 500 come from? The initial amount, and the 5 comes out, the minus 5 comes from where? Yeah, it's the net amount in the tank, right? There's 5 gallons of stuff coming in and 10 gallons of stuff going out, so it's decreasing by 5 every minute. So again, this is a concentration piece right here. We did ones like this, didn't we? Okay. That's basically section 3.1, setting up things as linear equations. That's 3.1. Okay. Another example they do in there, if you've got a physics slant, you might want to look at are circuits. And then they've got some other general modeling things, but circuits are also in there if you've got a physics slant with currents and all sorts of stuff. All right. Let me give you a couple of problems to look at. And again, these are more about setting things up more than the solving parts. This is 3.1. Look at 5, 17, 25, and 29. All right. They also, in the next section in 3.2, talk about nonlinear models. Probably one of the more famous ones that you have is what's referred to as a logistic model, a logistic equation. This comes up in population dynamics. And what I mean by that is certainly if you've got infinite resources and, say, no predators, the population of an organism, whatever it happens to be, should follow an exponential model. Okay? It should just be how many there are. If there's nothing to inhibit the growth, then it should grow exponentially. Okay? The logistic model comes up and saying, okay, well, that in practice, that doesn't make much sense, right? I could introduce, say, an invasive species on a small island. So why did I pick an invasive species? It has no natural predators. It just can grow unfettered, right? Okay. But eventually they're going to run out of, well, food, say, right? And then it's going to drop off. There's some sort of what that's referred to as a carrying capacity that's going to siphon off how quickly something can grow towards the end, right? So what you get with a logistic model is that the change in population at a particular time depends on how much population there is, but it's also going to depend on some other function of the population that's going to keep it from growing too far. They refer to this as what's called a density dependent hypothesis, what the book calls it. If you've got some sort of a carrying capacity to it, and they list this in the section as well, what this ends up looking like is that you'll have some function, some linear function of p. So you've got if it gets too big, it starts to make it curve down. So you get this quadratic piece on the right-hand side if you get too much. And that's where the logistic model comes from. I'm not going much into it right now because I'm not going to expect you to do a lot with modeling. I just want to show you that these things exist for nonlinear models as well. Okay. Another nonlinear model they talk about in the homework problems is air resistance for a free-falling body. A lot of times in physics, you do things in a vacuum. Things don't fall in a vacuum on Earth, so they got air resistance. So what happens is that your acceleration ends up getting slowed down by how fast the object moves, and it ends up being proportional to the square of the velocity is one model. And so for air resistance, you end up with something that looks like it looks like I'm just writing it down because they actually give you the formula in the problem. It's the mass times the derivative of velocity is mass times gravity minus something proportional to the velocity squared. And so this is what's affecting your air resistance. So the faster it goes, the more drag you get on your velocity change. And so you've probably heard of terminal velocity. That's what that limiting thing would be. Because eventually you're going to get closer and closer to zero and you can't cross it. It's going to be asymptotic. So that's what your terminal velocity is. And again, they mentioned that in one of the homework problems. So just to give you a couple of ones to look at in here, and then we'll be done. Literally a couple of ones to look at here. What in the world just happened? I have more problems today, as you've already noticed. In section 3.2, I want you to look at 3 and 17. 3 talks about carrying capacity for the logistic model, and 17 refers to the air resistance that I just mentioned. Look at it, understand what they're trying to do with it. Okay, just want to make sure you get a taste of it. Okay, I would be a really bad differential equation teacher if we didn't do some of the modeling. Okay, all right. We're not going to do 3.3 right now. 3.3 talks about modeling with systems. I will come back and look at that a little bit when we start talking about how to solve systems. Right now, we're just solving a single equation. So I didn't see the point of doing modeling with systems if we're not going to start talking about how to solve them. So we'll come back to 3.3. So on Thursday, we'll start with 4.1. We'll probably do 4.1 and 4.2 on Thursday. Okay. And like I said, we'll mention a little, my goodness, talk a little bit more about the exam on Thursday as well. So your exam, again, is a week from Thursday. All right. Have a good one. See you next time or in 15 minutes.